Till now, we have talked about affine spaces. We have talked about vector spaces and affine spaces. Vector spaces, when they are shifted, then we say shifted away from the origin. We say them affine spaces. Now, in machine learning, there is another concept to identify the similarity between two vectors is angle between two vectors. So we are interested in making a notion of the angle. So what does it mean by angle between two vectors? So with this aim, we are trying to start this particular portion, which talks about norms, inner product, distances, magnitudes, and angles. And finally, we will see some special bases which, if we take, then they they retain a lot of things with them. So with the aim of these things, we are going to start this part of the series. Okay, so let us talk about what is a Euclidean norm. Euclidean norm is the most basic norm, most widely accepted norm, and that is also called L2 norm, which is nothing, which we have all the time we use, and it is you take square of every component and you sum them up, and that is called the Euclidean norm. You take the square root of that, okay, and thereafter that whatever it the value comes is called Euclidean norm or L2 norm of the vector. Now when we say inner product, so the one of the most simple inner product is the dot product. And what is it? We multiply the vectors component wise. So corresponding components are multiplied and then summed up, and this is a particular inner product called dot product. So there are a lot of inner products, and out of that a dot product is widely used widely used product, inner product. And we'll see what does it mean by inner product and how this inner product can actually help us in doing things in machine learning, right? Okay, so any general inner product, because now we have talked about inner product, so we need to define what does it mean by the inner product. So any inner product is based on certain things. The one of them is bilinear mapping, another is symmetric, another is positive definite. So we are going to talk about these three concepts one by one. So first is bilinear mapping. Bilinear mapping. So any function omega that takes two arguments. So any uh, omega. So it's a mapping that takes two arguments and it is linear with respect to each argument. So what does it mean? It means that omega, if you take this one, so any linear combination of two vectors on the left hand side, left argument you take, then you can expand it as a linear mapping, similar to the linear mapping. Similarly, for the right argument also, you can express it as a linear mapping, and that's how it is called uh, bilinear, because for the left argument it is also linear and for the right argument it's also linear. So with if if these two properties are fulfilled, then we say that the mapping is bilinear. Okay, so the next thing comes out, that what do we mean by symmetric? So symmetric is easy. If you change the order of the argument, the value of the mapping doesn't change. So both the things actually goes to the same point, same value in R. So this omega, this bilinear mapping is actually going from, it takes two elements from the vector space. It takes two elements from the vector space and map them to a real value. So definitely it's a many to one uh, mapping. So a lot of vectors, a lot of pairs actually maps to the same real number. So which right, so that's what it happens. So we have two items from the same vector space V. So these two items are basically belonging to the same vector space V, and if you map them, then it holds the bilinear mapping, and it should be symmetric. And then what does it mean by the positive definiteness? So for the positive definiteness, what is said, if you have two vectors, if you have a vector, if you have a vector, a particular vector x, which is not zero, especially which is not zero, and if you pass that particular vector in both the arguments to the bilinear mapping, then it should be non it should be positive. It should be positive, and it can be zero if and only if both the vectors that has been given as an input are zero vectors. So if the vector is zero, entirely all the components are zero, then only that this mapping leads you to a zero value. So if that is so, then we say it's a positive definite. So for inner product, we need to have three properties. First is bilinear, the second is symmetric, and the third is positive definiteness. Now, so this is the definition. We said a positive, definite, symmetric bilinear mapping that takes two argument from the vector space V and maps them to a real number, and that is called the inner product. And there is a small definition again. So you say that a vector space V, when you say that it is equipped with some inner product, then it is called inner product space. And dot product is one of the special inner products. And in that case, so whenever you use dot product as the inner product with vector space, the real numbers or Rn, then this inner product space is called Euclidean vector space. So if the inner product equipped with Rn is dot product, then we say that it is a Euclidean vector space. Okay, so let us take an example of an inner product which does not look like the dot product, because we know that we have seen a dot product, but what other kind of inner products do exist? So let us just see that this particular thing, whether it is a inner product or it is capable of being an inner product or not. So check it out, that if you replace, if you want to find out, instead of xy you want to find out yx, you will find that this is exactly same. So there's no problem, and it is symmetric. Similarly, you will find that it is bilinear as well. And the third thing, that it is positive definite. For being positive definite, you just keep x in the product and club these x1 square and x2 square terms, x1 square term with all the x1 x2 x1 x2 terms and all those sums. So if you club them up, you will definitely reach to something, some expression which says some expression whole square plus or minus some other expression whose whole square, which will let you know whether it will be always positive or may not be. And if that is the case, then you will say okay, it is positive definite or not. So let us see symmetric positive definite matrices. So when we talk about definite positive definite matrices, because as of now we just talked about the positive definiteness of the bilinear mapping of the inner product. Now we are going to talk about the positive definiteness of the matrices. So this particular idea I'll take it in the next video. For this video, thank you.